more multiple choice questions on KP. Question 14. The equilibrium mixture is prepared in a container of fixed volume. Temperature of this mixture is decreased and the mixture is allowed to reach a new equilibrium. Which is greater for the new equilibrium than for the original equilibrium. The mole fraction of carbon monoxide. Well, let's read it again. Temperature is decreased. Temperature decreased. Forward reaction is exothermic. So if the temperature decreases, the backward reaction is endo. Temperature is decreased, you're going to shift to the side to increase temperature, aka the exothermic. So therefore, we've got more of this COCO2, higher equilibrium yield of that. So which is great for the new equilibrium. The mole fraction of carbon monoxide is greater. That is false. The partial pressure of chlorine, no. The total pressure of the mixture, could be, and the value of the Kp. Well, Kp is going to be the products divided by reactants. So if I've got more products, I've got like 100 divided by 10 compared to if I've got 1,000 divided by 10. Which one's going to be the bigger value? It's obviously going to be this one. So the value of Kp would actually increase. So therefore C is obviously wrong as well. Question 12. Okay, so this equilibrium at temperature of 585 Kelvin, total pressure of 540 kilopascals occurs in a vessel of volume of that. At equilibrium, the vessel contains that much of SO2, that much of O2, and that much of SO3. With pressures expressed in MPa, the value of the equilibrium constant Kp is. Okay, so it does look like a difficult question, like because of this, like there's no reason to put that in. There's no reason. Okay, I'm gonna cross that out and let's see. I'm gonna calculate the answer and then let's see if I even needed this table or not. So Kp, I need the partial pressure. Curly, remember, it's not square brackets, it's round brackets of SO3 squared divided by partial pressure SO2 squared times by the partial pressure of O2. So now I know what my expression is, what I need to do. I need to find the partial pressure of that. How do I do that? Well, usually, obviously, I'd go ICEMP. But I've already got the equilibrium moles at equilibrium. So all I have to do now, and this is why it's a one marker, it's not going to make you do like 5 steps, maybe 3 or 4, definitely not 5. So I've already got the equilibrium moles. So ICE MP. So what I need to do is find the equilibrium moles I've already got. 0.050 of SO2, 0.080 of O2, and 0.0700 of SO3. Now the mole fraction, all it's going to be is the number of moles of what I have. So SO2 0.0500 divided by the total number of equilibrium moles. And I'm just going to do that, work that out first. The total number of equilibrium moles plus 0.0800 plus 0.0700. It is 1 over 5, 0.2 moles. So it's going to be 0.0500 divided by my answer, 1 over 4. It's a mole fraction of SO2. O2, 0.0800 divided by 1 over 5. 2 over 5. And a mole fraction of SO3, 0.0700 divided by 1 over 5. 7 over 20. And if I add those three up, 1 over 4 plus 2 over 5 plus 7 over 20, I get 1, which is correct. So that's correct. Now I've got more fractions, but I don't want that. I want the partial pressure. So what I need to do is I need to times by the total pressure. Now, I'm not sure. Do I need it in Pascal? Yeah, pressure is always measured in Pascal, so that makes sense. So, yeah, I want it in Pascals. So, times by 540,000. So, 1 over 4 times by 540,123. I do want it in Pascals, right? Yeah, because it says right here, MPa units. So, I need it in Pascals. So, there we go. So, I've got 135,000 Pascals for SO2. SO2 2 over 5 times by 340, 540, 1, 2, 3, 540,000, 216,000 of O2 and SO3 7 over 20 times by 540, 1, 2, 3, 189,000 of SO3. And now let's just add them all up. 216 plus 180. Is that 180? 189. I do get 540, so that's correct. Now I just substitute it in, right? Yes. Yes, yes, yes. Because the volume is that, but it will cancel out anyway. So SO3, 189,000 squared, divided by SO2, 135,000 squared, times by O2, 216, 123. That's not squared. And I get 9.07 times by 10 to the power minus 6 MPa units. Nine point oh seven, but I got 9.7 times by 10 to the power minus 6. Let's carry on. Possible units for the equilibrium constant Kp include. So Kp is product. No, it's not. It's partial pressure of SO3 squared divided by partial pressure SO2 squared times by partial pressure of O2. And I know, given in the question, that the possible units for the equilibrium constant. So I've got stable working rate kPa, kilopascals, total pressure kilopascals, kPa squared divided by kPa cubed. So I get 1 over kPa, which is kPa to power minus 1. So no units, that's false. kPa, that's false. MPa to power minus 1, that's true. Because that's what I did if it was kPa, kilopascal, but possible units it says. So if it was MPa, then yes, definitely, because it's the same process, same method, and it would just be M. And kPa to power minus 2, no, we clearly see it's to the power minus 1. And then question 10. Okay, so we've got the temperature originally, yeah, this equilibrium, total pressure, we've got the volume, we've got the equilibrium moles, so we've got everything basically. We've got then at equilibrium, same vessel or volumes are under altered conditions, the reaction mixture contains a different number of SO. No, they've all got, no, they haven't got the same number of moles. At total pressure, something slightly different, the temperature is. How do I find the temperature? Well, temperature is gonna be I've got a method, but it's a risky method because the method I'm thinking of is finding out KP for the original one, and then finding out KP afterwards, and then obviously I can I if delta H is actually, let me find out if delta H is negative or not. SO3 squared minus 396 times by 2 minus 297 times by 2, and obviously oxygen is 0. It is delta H is negative. It's negative 198, and that is actually really, is it really important? I don't know, but that means if the temperature, okay, so let me do what I'm thinking. Find out KP for this equilibrium and this one. Well, KP for this one, equilibrium vessel contain that much moles, that much moles, that much moles. And you find a mole fraction, and then you tell by total pressure, and then that's the moles. And I want the, yeah, okay, so let's do that. So it's going to be 0.0500 times by 540,000. Got 270,000, 27,000. I've got 0.0800 times by 540,000, 43,200. 0.0700 times by 540,000, 37,800. And that is for SO3. That is for SO2. That is for O2. That is for SO2. Now to find out the... No, I need to find out the mole fraction and then the partial pressure. Okay. Well, it's probably going to make sense to just draw out the table. Just get it done. This is the last multiple choice question anyway. Mole fraction, pressure, or let's say partial pressure. So I've got 0.050 divided by 0.0500 plus 0.0800 plus 0.0700. 1 over 4. It's the same as 1 over 4. And then for oxygen, well, we just change the top to the normal moles of oxygen, which is 0.080. 2 over 5, SO3, 0.050. 1 over 4. Add them all up. 1 over 4. 1 over 4 plus 2 over 5 plus 1 over 4. That's wrong. That is wrong. SO3, 0.0700 divided by 0.050 plus 0.080 plus 0.0700. 7 over 20. And that makes complete sense. In terms of my pressures, I can get KP. Or do I... Or what? Why would I... Surely I would calculate KP for the second condition, because then... No, let's just... I don't know what I'm doing at this point. SO3, 7/20. But one thing I'm going to tell you guys, I'm not going to give up. I either get it, I don't want to give up. Squared divided by 1/4 times by 540, 1, 2, 3, squared times by 2/5 times by 540, 1, 2, 3. I get KP as 9.07 times by 25 minus 6. So, you can make sure that temperature. I ain't giving up, that's for sure. Maybe I didn't even have to do all of that. Because remember, Kp is the partial pressure of SO3 divided by that. So, if I have, oh my days, if I have more moles of oxygen, I'm going to have a higher mole fraction for oxygen, and therefore the products divided by the reactants, well, therefore I'm doing the same number divided by a bigger number, and therefore I'm going to have a smaller number overall, like 100 divided by 10 is 10, 100 divided by 50 is 2. I'm going to have a smaller number. Therefore, Kp is going to decrease. Oh my days, I didn't have to do really any calculations. Kp decreases in the second condition. And the temperature, well, the forward direction is negative, so I want that. So, increased temperature is going to shift to the endothermic direction. Yeah, so I'm looking for one that is a high temperature than 585 Kelvin, 596 Kelvin. I'm not sure for this one. Let's mark it. Question 14D, I expected that. Question 12C, expected that as well, even though it was a mistake. Question 11C, again I got that right, but just last one, question 10D, 642 Kelvin. Why is it that? Because I clearly got a higher number of moles of oxygen in the second condition. I've got a total pressure of that. So what's going to happen to the Kp value? It's going to be smaller in this one. The Kp value is going to decrease. And if the Kp value decreases, well then, yeah, Kp value decreases. Temperature. Or do I do... I'm sorry guys.